Ray Poovey since we were 19 years old.
Oh, really?
And we've had dreams that span all that time. You might notice we're not 19.
Well, they're 26, but we're going to let that go. So anyway,
He truly is Irish.
let's let these guys, get into the thing. So we're going to go, with Dell and Dr. Poovey, and then maybe you do cleanup for us.
Sure, I'll be
All
glad
right,
to.
good deal.
Pleasure.
Dr. Poovey. Imagine two guys meeting in Dunsmuir, California, both of us having a photonic switch.
Amazing.
Gosh, isn't it God wonderful?
It is.
Let me tell you this. I'm going to tell these people how a transistor works briefly,
Okay.
and then you tell us what you can do with your switch. For a long time, people knew that you could take electrons into a silicon chip that had negative doping, which meant that it had too many electrons, and put a chip that didn't have enough on top of it. And by itself, those chips would allow electrons to flow that way, but not the other way. Because as you put electrons in here, these electrons would be like they want to be somewhere else, so they would go that direction, because electrons repel electrons. So as they got closer to here, they'd find a hole and they'd jump across that hole, and then another hole would come in here moving that way, and these things would just kind of absorb each other, and you'd have good electron flow. If you were to try to get the electrons to go this way, what would happen is a hole that might be here would be attracted to this first electron that would go that way, and an electron that might be here would be attracted to the hole down there, and you'd have this region in here that would be depleted of electrons.
No electrons.
No electrons in that region, there's no flow. So suddenly, you've got a diode. It's a one-way device. We all know people who are one-way devices. Okay, it works one way, it doesn't work backwards. So they felt like if we could only find some way of controlling that flow. And to do that, they came up with this positive material here, negative material here, all silicon. And if you put another one here, that's silicon. Now if you put a big positive voltage there and a big negative voltage here and a negative voltage here, more than this one, this guy would say, no, I don't want to go there, because the holes would go that direction, electrons would go that direction, and then you'd have that depleted region and there'd be no flow. The diode is off. But if you put a little bit of a positive voltage here, current would start to go that way and recombine like we showed for the diode. But that opens up this gate, and some of it would go this way, and so a little bit of current going that way could control a lot of current going that way. And it was variable. You could control that, turn it off and on. That transistor is what changed the world. Its symbol is this. Okay, this is the gate over here. This is the emitter. This is the collector. And I spent years at the postgraduate school in Monterey teaching people how to put these into circuits, how they work, why they work fast, why they work slow. And during all of that time, there was always a limit on how fast you could turn this guy off and on. This is what makes computers slow. When you tell this thing to come on, it has to start here in order to get that started, and this thing right here is called rise time. You can't make the thing any narrower than that, because it has to have the rise time and fall time, and so that would determine how quickly you can clock the computer or anything else. You could make better, faster, faster, better, but you couldn't overcome this. If we only had something we could turn on and off faster, we wouldn't have to have a lot of heat. And now here's where there's heat. This is a very important point that's never been brought up before in this room. Okay. A transistor that is off there's no current flow. If there's no current flow, then whatever this voltage is here is the same as right here, because there's no current flow and there's no heat wasted. It's off. There's no current. Now a transistor that's on, all the way on, like a big positive here, has this flowing in it, And it's very interesting because this would be 5 volts and this would be 0.3 volts. Okay, now you've got a lot of voltage across here, but have very little voltage on the transistor. So even though you're using a lot of power, the transistor is still safe because it has very little voltage across it. Now, so having it all the way on, all the way off is no problem. A transistor can handle this very nicely. A transistor can handle this very nicely, but it doesn't like it right there. Now you've got voltage across the transistor. You're halfway there. Half of the voltage is on the transistor and half of the current. And when you multiply voltage times current, you get watts, power, lots of watts. So if you try to do this fast like this, that transistor gets too hot and burns up. So you have to go like this, and then wait, and then do it again. So that from this point to this point, the percentage of time that you're on is very low so it doesn't get too hot. Always having to slow down and wait for the heat from the transistor. What if we'd had something that didn't have to create heat? Dr. Poovey.
So the idea that God gave me was that a piezoelectric element could be in a fiber optic channel, and the fiber optic element could respond to a wavelength of light. The electric field of light will make the piezoelectric element contort like this and change, let's draw it again up here, and change the channel so that the message light would be cut off, would be stopped. When this light comes through, it shuts off the data light. So this is the idea that when, well, I'll draw it one more time. Here's the data light is going through, and the switch is off. Then you send in the switching light, and the piezoelectric contorts and it shuts off the data light. So a light is able to shut off a light. And instead of driving electrons through silicon, it's a crystal response to an electric field. The electrons and parts of the crystal move a little bit in the crystal. They just shift position a little bit. It changes the shape of the piezoelectric and shuts off the signal light, which is a longer wavelength. So now, instead of driving electrons through a silicon and generating and producing a lot of heat, using a lot of watts, the voltage of the light causes the crystal to respond and it switches. So the switching process is completely different than the electrons being driven through silicon. The response of a crystal is what makes this switch work.
Now let me tell you how that attacked me when I first met Dr. Poovey and we started talking about this switch of his. If I were to say that this was the emitter on a transistor and this was the collector on the transistor and this was the base, I could put a little bit of a light down here that was always showing light. That would be his data light. And then I could say, when I do put light in here, this light up here would go off. That was coming through here all the time. So that makes this thing switched like a transistor, but it's using light and light only. And it can have this symbol, and we've created this symbol as the international standard for our light switch. It's got an incoming light, it's got a data light path, and we control it. That incoming light hits that thing and moves it and causes this to start or stop. Now, so that symbol for computer logic is this, it's an inverter. On an inverter, whenever you turn something on, what was there goes off. Those are the simple things. Using that inverter on other logical light can do some very interesting things, and right off the bat, we started talking about how we turn this into computer logic. One of the simplest of those is, let me show you two fibers. They combine like that. And if I were to put the Povey switch right here, now if I had this signal on one fiber and this signal on the other fiber, at this point I would get a signal that was one or the other. So here we have an OR gate. Either one of those will give us a light out. And if I put that inverter here, what we would have would be this. And that would be called a NOT OR gate, or NOR.
NOR gate.
That is the first and simplest of all computer logic elements, is a NOR gate. But there are other ones much more important than that that'll let us do things that that's by itself can't do. Now, Dr. Povey just informed me a few minutes ago that not only can this thing switch the thing off and on, but it can also control how much, which opens an entirely new field of photonics for us that we hadn't considered.
If we use the switch in combination with a doped, an erbium doped channel, this is what they use in fiber optic communication across the country. They put an erbium doped portion of the channel, and it will be excited by a higher frequency, and then when the signal light comes in, if it's low energy, it'll be boosted up. So we can boost up the power using erbium doped fibers. Not just erbium, there are other, but erbium is used commonly. An erbium doped fiber will boost power up, and we can use it in combination with the switch to have power control as well.
Now, I'd like to ask Richard, how fast do you think we could turn this off and on? And what's the experience been so far? And what is the mathematical implications of that?
Certainly. I'm a data scientist, and by trade, I help build various data centers for Kaiser, for Oracle, for Intel. I've worked for NASA. I've done all of these various corporate jobs, and one of the things that has driven that is speed. It's all about speed. It's all about processing speed. You've heard about Moore's Law?
Yes.
Any of you? Well, let's look at an exponential curve. Well, we're going to try to look at an exponential curve. And somewhere back in the 50s, you have a transistor, first transistor. And it is, okay, and it is 1953, and Shockley and Bernstein, thank you. Well, I'm going to get one of these right. And we have three of them, and they produce a point contact transistor, and they get the Nobel Prize for it, for one transistor. And it switches off and on, off and on. And it doesn't do it very fast, but it does it faster than the vacuums, the vacuum tubes that were in its place. And so you take a computer that was the size of a room, and you shrink it down to the size of a large desk or a small room. And instead of, you're now, instead of using a city to power it, you're powering it with off the grid and a couple tens of thousands of volts. But in any event, you're here. Now, when I first got involved, I wasn't here. I was in 1976. So I'm somewhere here. Somewhere here. A lot of work went into making that off and on much faster.
What is that up there?
Up there is a zero state.
I mean, what is this?
Oh, this is the curve of speed.
Speed. Oh, right.
Okay. This is the curve of speed. I'm sorry, I didn't mean to be
No, no problem.
opaque.
That's
Speed on the
okay.
vertical
I got it.
and time
Thing.
on the
And
horizontal.
The development.
And so we got a vertical axis, and we're climbing up here so very fast that this becomes what they call asymptotic. It becomes closer and closer to being infinite, right? And so where are we on this curve, and where are we going to be on this curve? Here we are, progress made. Here we are, and we've gone from 1, and now we carry devices with 1 billion circuits on it. And it's held in our hand, and we talk anywhere in the world on this device.
Let's call that 2000 right there.
Yeah.
Okay.
So, where do we want to be? Well, I believe we started off with milliseconds, and we started progressing to what would be appropriate. Well, let me just jump to here. We're talking about 10 to the minus 15. How tiny is 10 to the minus 15? Now we're talking about the time that it takes a wave of light to go across an atom. That's what we're talking about. Think of how incredibly short that time is. Okay, where do we want to be? We want to be in femtosecond speeds. Where are we now? We're about 4 to 4 magnitudes, less than that. We're at about 10 to the minus 12, Gary?
9.
9
Nanoseconds.
nanoseconds. Okay.
Now let me give the classroom postgraduate school talk about the time for just a
Absolutely.
second.
Elaborate, doctor.
Okay. The old
And you can
vacuum
have that
tube-
pen too.
The old vacuum tube had a cathode. That was the beginning where it came in. Had a grid to control it, and it had this plate up here to collect all the electrons that were going up there. And they'd be turned off and on from there. And this distance, those electrons had to travel at about half the speed of light. Okay.
All right.
So it turned, there was another problem. Every tube had to have this filament.
A heater.
It heats that cathode up to make the electrons float into a little cloud of electrons here. And that took more power than today's computers. Just
to do
one,
that. Just to do that.
one hill.
One tube.
So the tube systems of those days had thousands of tubes in them, and they had to replace dozens of them every day because of the failure rate. But it was really this distance from here to here that everybody knew was the thing that was keeping computers from being fast. So when the transistor came along, and by the way, the transistor is the same thing, a controller and a plate, but they don't need a heater. They immediately got rid of 80% of the wasted energy. And the distance from here to here was thousands, 1,000th or so of what it used to be in the tube. So now they could go faster, where a tube used to go like this to be turned on. The transistor could do it like that and be turned on. So imagine from then on out, from this period of time to about here, the whole idea was getting this guy thinner and thinner to make the distance from here to here decrease so that that speed would go faster.
And now we're talking about devices
Yeah.
that measure, put 1 billion of them
Yeah.
in a chip that
Now,
size.
you
and
also
we're
have-
talking about 5 nanometers of distance.
Yep.
And you also have to have these little traces on board the circuitry to carry power in and out of there. And these things used to be like that and long, but now they have to be narrower and closer together because this transistor and another one up here doesn't help you if you can't move that one closer.
Now,
Yeah.
that all sounds great in terms of speed and performance of where we are. You think, well, why would we want to go here? Why would we want to be so much faster? It isn't fast enough. Well, I build data centers. I built one in Napa for Kaiser. And so what did that data center do? It enabled anybody who has a Kaiser card and go in and they get their medical records immediately, real time. And that was supplied by data centers all over the country. I helped build the Napa data center. And so you go on the Napa data center and you think, well, how big is that? You could make a nice, how would you say, 2 or 3 times a roller skate ring kind of deal. You literally roller skate from one end to the other. And guess what? It took megawatts of energy and an incredible tens of thousands of BTUs cooling to deal with the megawatts and megawatts of energy that you're saying. There more energy is used by that one data center than all the rest of Napa and its 50,000 inhabitants. So one data center. And guess what? They're a small data center compared to Google. And that enables us to, how do we save the 2 things that mean the most in terms of a data center? Cooling and electricity to drive this whole process. You eliminate those 2 things and you reduce the cost of operation down. Down by orders of magnitude to get that extra speed. So speed is the thing you want. Speed is what Gary Switch is going to do.
Farm. Okay.
I won't.
I want to tell you this. Mr. Bailey has 2 other video recordings that have been put together showing how we make computer logic out of this. Dr. Poovey and I talking yesterday about how to speed that up, what the goals are, and those will be available through Mr. Bailey if anybody wants to know more about the details and the secret sauce of what we're doing.
Just before you finish, just talk about how you put multiple switches on a board to make a,
I will do that.
I mean, not the whole farm, but.
I know. Okay, so Dr. Poovey is a plasma physicist. He's been helping people like Intel run their foundries to reduce things down. Things get deposited through an electron beam to a silicon chip, and they can put that through lithography, just like making a photograph, and create layers of things. So what he's going to be designing is a chip that has, it'll be a round chip, but on that chip there'll be a place that has cut slices through it for light to go through there, and there'll be places where we deposit different materials. And I'm going to let him tell you how that's done in a minute, but what our goal right now is that we want to put on one of these chips a gate going that direction, one going that direction, one going this direction, and one going that direction. And then we'll do that 2 more times, so that this chip has 8 switches. Now, on here, there will be other chips like that, up to maybe 10. And those, though, but now that chip can be taken out by itself and put on a light board like you saw next door here, and we can connect up fibers from here to here, here to here. Some of them come back in and come on back like this. And we're going to connect this NAND gate here and this NAND gate together like this, such that this one comes over here and feeds that, that one comes over here and feeds that, and then this is a control line, and then we can take a look at that as data or that as data. And this device by itself, just 2 of these, will always have light going one way and none on the other side, unless we introduce a little pulse of light here, which would make that one go off and that one come on. And then it would stay that way until we changed it by putting something in here. This is 1 bit of information stored in light with no electron flow.
No heat.
No heat, very little power. And I think there's a lot of secret sauce on how we're going to do this.
Yes.
That should probably be a second video.
Yes.
Yes, sir.
So would that be like a switch then? Or
Yes, this is a switch. Remember, whatever is true here will be non-true here. Okay? And what we're doing is we're building we actually have a patent pending on just this, the NAND gate. That patent pending is a very complex piece of circuitry on here to give us a situation where only when you have something here like this, at that point right there, we would have no output. Because this was not AND, that is AND, that's not AND, and so it gets inverted so that the output then is NAND. And that then in itself, two of those put together back to back can make a flip-flop. A flip-flop is the basic device necessary for any computer.
There is a universal set of gates,
Yep.
of which
Yeah.
the XOR gate and the AND gate are fundamental. From those two gates, you can build any logical circuit that you wish to have. And what that translates to is that you can basically do anything that a classic computer does with electrons,
Right.
and you can do it with light.
I had the opportunity for another physicist to walk into my office about 3 months ago, looked at our work and said, "What are you doing with the Michelson interferometer?" And I said, "It's not a Michelson interferometer. It's a double delay line, helps us turn light off and on with light." He looked at me and said, "Well, that hasn't been done yet." And I said, "It has, and we have patents."
There you go.
Okay.
Good.
Yeah.
Very good.
Anything else to say? So, yeah, just to wrap this up, because like Dale said, we can't give away like all the sauce, right? But I think we've shown you enough here to make the people who know me understand what I said when I said we wanted to be the most significant carbon reduction company in history. So what you're going to learn as we go forward is, like Dr. Klein said, data centers actually produce 80 times the carbon of automobiles. So, you know, we're in the automobile business, and certainly we're trying to reduce carbon by going from, you know, gas vehicles to electric vehicles. It's just a little thing. That's a little thing. What we're talking about today, literally, in my opinion, is the most significant technology in the world. That sounds like a big statement, but I started off giving you a comparison to the transistor. And what we have is a history that changed the world using the electrons. And now we're talking about similar devices that could be as high as what, 1,000 times faster?
Yes.
Yeah.
1,000 times faster. So what does that mean for cracking codes for the military? What does that mean?
Don't want to talk about that.
We don't want to talk about that. But if you're in the data center business and you have a $500,000 a month electric bill, maybe we cut that bill to what?
Fraction.
A fraction. A fraction. And what Ben Franklin said, what, a penny saves, a penny earned, right? So just on that alone, I think you guys can really understand the potential. I think hopefully you understand that this is not ground floor. We haven't built the floor yet. And so over the next couple of weeks, I'm going to be talking to some of you about how you can get involved and how you can get in this early enough that you can be involved. This is actually a big boys game. This is something more of a conversation for, you know, already multinational corporations to be having a conversation about. But a lot of you guys are going to be glad that you know me and that you met Dale and Dr. Klein and Dr. Povey, because we're going to give you some opportunity before we build the floor, right?
Good.
Patents are already pending. You know, the work, the demonstration projects are here. And so the next step is an easy one. The next step is really about educating you guys as to where we are already. The story of where we're going is almost fantastical when people really understand where we're going. But I think you'll really be impressed with where we are now. So you're gonna wanna tap in, you're gonna wanna follow us, you're gonna want to just like watch and share with your friends every single thing that we're doing, right? So stay in touch and we'll talk to you soon.